Okay, so we were here trying to solve this problem of putting straight perspective issues. So, and in general, this is just an excuse to introduce this kind of geometrical transformation. So we have this perspective, and then we want to make it straight. So which is the transformation that takes coordinates from coordinates. Say that this is our output. And we take this coordinate, and we have to find where it is coming from in this. So this geometrical transformation applies on the coordinates. Okay. Coordinates of J, and they give a coordinate I. And then we argued last day that we were trying to look for the transformation of this function. But I think it changed. Okay. And this was 2 times 1, this was 1 times 2, this was 1 times 2. And we saw that we didn't succeed to make it. We did it a little bit better. So this was the original, and this is sad. So we did it a little bit better. Red is where it was, blue is where it wanted to be. So it is a little bit better, but not so much better. So why? Because perspective is something that happens in 3D, and our transformation is only dealing with 2 dimensions. So let's try to modify the problem so that it is now expressed in a 3D way. So, and for doing that, what we did was to extend the coordinates and now use homogeneous coordinates. The homogeneous coordinates is you have a coordinate that we use tilde to represent the homogeneous coordinate. This is ABC, say, and this corresponds to a specific coordinate. So this is B minus 1. And this corresponds to a specific coordinate that will be A divided by C, B divided by C. This is the dimension. So in this direction, it is unique. So given one homogeneous coordinate, you only have one two-dimensional coordinate. But in this direction, it is not unique. So given a 2D coordinate, we have infinitely many homogeneous coordinates that represent the same point. And why infinitely many? Because you have to choose this C. If you choose C equal 1, then you have one coordinate. If you choose C equal whatever, then you have some other coordinate. So now we will make the same, or we will pose the same coordinate system, but now in 3D. Now this will be 3 minus 1, 3 minus 3, 3 times 1. And remind that we don't have only one correspondence, so we don't only have a couple of points. You have many points. So you have this point goes to this point goes to this point goes to this. Then with all those points, you can put the matrix. Then you can say, I will construct the matrix. I will have Ri1 multiplied by 8, 50 Rj1. And then, so this is a pair. And then I have another pair. So I have I2 And this goes to a and all the pairs that we have. Now you have a matrix, let's say, now the name in the slides, so you see now the name is not the slide. But this matrix has this form. But this equation system has this form. And let's put sizes to these things. Sizes, the sizes. So this is 3 times b. 3 times 3. This is again 3 times b. So we know how to solve for this h. Okay, so let's see. We will solve for h in a different way. So this is we could use Lisa squares, but we will use a different technique to solve for h. Okay, so yeah, this is the formulation. So we have homogeneous points in one of the images, the homogeneous points. So this will be going from K to I. So here the points, so this will be x, y, 1. And then when I transform, I multiply by h. In general, here they will be whatever. They will be x, y, z. Because the h is breaking this constraint to be 1. So this is a third homogeneous coordinate. After multiplying by h will not be 1 anymore. It will be whatever. So this is what we have here. So we start with coordinates that have 1, and then we multiply this by the matrix H, and then in general we get any homogeneous coordinate. And we have represented the homogeneous coordinate in this way. So Ki, and then A and B, they are Ki, Dy, Ki, Bi. Okay, so now we will have a collection of these kind of points. Okay. Now, let's look at a single one of these correspondences. So let's try to modify it. So this is just the same equation system, but now it is written more explicitly. And then we solve for u. So we divide the first equation by the third equation, and the second equation by the third equation. This is what we get. We divide first by last. This is what we get. Second by last. It's this one. And then there are too many degrees of freedom. So because of these infinitely many that homogeneous points that correspond to a single hypothetically, there are too many degrees of freedom. So you have to fix something. And the way to fix is we will set H3 1. Okay, so set H3 1. And to do that, what we will do is to divide here by H3. So you divide H3 here, H3, now you have 1. And in the numerator, what you will have benefits. If you do it in the slides, the whiteboard. So we had one of the equations was u I is equal to H11 x xi psi. That's H12 y plus H3 like here was H V1 X I H V2 I X V1. Now we divide by H3 everywhere. So if this divide by H3, this we divide by H3. Now this is equal to this would be H11 divided by H X 5 H1 divided by H between 5 that's one. That's H 1 divided by H between then the same. So now this one you can call it H11 prime. This one we can call H12 prime. The same for all of them. So now what we have is a matrix H prime. H prime is H11 prime, H1 prime, H1 prime. Always. H3 prime, H3 prime, and then 1. This is there. This is what is prime. Okay, but now we don't care. We didn't have H either, so we don't care if it is H or H prime. So, something that is very typical is now I will call this again H. I didn't have H in anyway, so I will rename it. But this is what has been done here. So you call it H prime, but then you relabel the coefficients. You rename them. You have, but this H11 is not this the same H11 here. But we didn't have H11 anyway. We have to find it. Okay, so and now you recognize these are the coordinates in the image I. So the 2D coordinates, not the homogeneous coordinates. Okay. This is homogeneous. U and V, they are not homogeneous. They are the two coordinates. Now you have transformed X and Y coordinates, the J image to U and V coordinates, the I image. Okay, now you rearrange this thing. Take this to the other side. You rearrange it. And part more rearrangement. And then you write as a matrix form. Okay, so here, which are the nouns? The nouns are the H. This is what we want to form. And what is the noun? So the noun is X, Y, U, and V. These are the pairs of coordinates. So this matrix, we know everything. This H is our noun. This one is the H3, and then it is equals in. And this one goes with these coordinates. Okay, so you could take just the part that is unknown and take this U and V to the other side, and then you have it in a more standard way for you. Okay, so here we have both. We have the nouns, and so we typically write something like AX equal B is the vector. We'll also write A minus B, then multiplied by X equals 0. So what we have written in the slide is this. The constant has been put into the system matrix. This is everything. Why? Because but this one is related to homogeneous coordinates. It's coming from the homogeneous coordinates. So because in the homogeneous coordinates we have so much freedom that you have a point and then you have many homogeneous coordinates that represent the same point. You are trying to fix it somehow. So, and this is the fix this time. So it is to have H3 for 1. Okay, so we have to solve for 8 in this equation system. And then you have all the pairs. Now you have this equation system. So all this A times H equals 0. This 0 should be vector. Should be both. Okay, then, so you may remember this SPD that was introduced last lecture. So SPD is a way to decompose any matrix. So you can decompose any matrix as in multiplication of Q times S times B transpose. So U and V are unitary matrices, so they are notations. And S is the diagonal matrix. Here it is shown only for square matrices. So if it is not a square, you will have more zeros on one of the side square. For a square matrix, it looks like this. Okay, so we have to solve this problem. A times H equals 0. So a possible solution is to take this singular value decomposition of a find the smallest singular value, and then you take the B that correspond to that smallest singular value. So this is kind of eigenvector, right? It's not eigenvector, it's singular vector. It's a singular vector that is the one corresponding to the minimum singular value. And this is H. Okay, so when you have, this is a result from algebra. When you have solved a system like this, then a possible way to find the solution is this one. You make the SPD decomposition, and then you find which is the smallest singular value, and you take the B vector that corresponds to that singular value. And then this is your H, this B that you have found. You found this B that we have found, that is your H. And then you can go from J coordinates multiplied by H minus 1. Okay. So you know the difference between H or H minus 1 is in which direction you're going. So either H goes from here to there, you go in the reverse way, this H minus 1. So it doesn't matter in which way you define it. This end is completing the neighborhood or interpolation. So we have seen the bilinear interpolation, nearest neighbor interpolation. These coordinate will be fractional and data. So you have to find the value of I at that location. So that will be your value that you have to compute. Yeah, so yeah, this end, yeah, is this normalization by Chinese from negative. This is not interpolation, this is the normalization. You take in general this continuous coordinate, divide by the third element, so you find which is the coordinate the input image, and now you have to interpolate. So N is representing the normalization, it is not representing the deformation. Doesn't show the results, but hope that they are better. Doesn't show for this particular problem of the tower. Okay, any questions? So now we have seen another way of solving this equation system. So the first one we solved was this squares. Now this is the second one using SVD. Okay, so the last part of the lecture is about image rotation. So image rotation is done by this matrix here. By this transformation. So this transformation is like it. Yeah. We write it in the same order as this one. Pero I will use some white. I think this for that x out y minus x out so zero minus y out. Sorry, that let me put the same sign as the slides. So now we have on out our input image that we go in. So with this definition, we are going from this point, this direction. This transformation, the way we have defined, goes from the input space to the output space, so it goes in that direction. And this is a rotation matrix. So here we see this structure. See, rotation matrix. Now we have here R out minus R out. So that means we choose center in these two images. So we define a center. This point, at least 2 points. Okay, these are these 2 points. When you choose an origin to rotate, now you rotate. Now, rotate so that any coordinate is rotated with respect to this origin. And we have seen this structure another times before. This is just changing the coordinate system, so to shift the coordinate system somewhere particular to these 2 points. Then you apply a transformation, and then you This is really, really difficult. So first you define your coordinate system, where it is, and you apply transformation, and then you undo. And so this is our transformation. So see, I have written this on the side, then it's more clear the stack element. And then you rotate this like this. There is a problem with the corners. That is, let's say that the green is the input image. So when you rotate it, parts of it comes out of the image. And some of the parts in the output image, they are not defined. What happens with this corner? Here, here, they're not defined. So what do you do in the corners? You can put 0, you can put vacuum if you want. Instead of just rotating this image. You can do the same thing as in the Fourier transform. So you have an image. Have an image, but then you make it periodic. Copy. The same image. So one of them will be the central cost. But when you rotate, everything is 30. Everything is 30. And then you have something, so you have another copy here. So now this part is defined. So dealing with borders, it applies always. So those apply with the previous transformation pattern. Okay, so at the borders, you will always have these problems. Parts of the image, of the input image are not represented, and parts of the output are not defined. The part that you care is typically the undefined ones. This one is goes that's all. But you don't like these undefined regions, and you have to do something there. Either you put 0, even some people, some applications, they put not the numbers, just to say this is not defined. Or you make some kind of wrapping of the image. But you have to deal with the problems. And then you may also wonder, okay, let's say that I want to keep the full image. So I want to keep all the input image. So I have to make it big, an image that is bigger. So now I will extract the output will be bigger. So this is another possible decision. And then all the equations here that we have there, all the details for this handling how much bigger is bigger, so on. But we don't care about this. So all we care is this notion. When you apply transformation, a geometrical transformation, part of the input may go outside the original size. If we want to keep them, we will need a larger canvas or there will be regions in the output that are undefined. Have anything there, then you have to deal with the borders, and you have many choices. This repetition is one of them. That is, you can also mirror. So let's say that this image has some distinctive thing. So you can mirror on this edge. Here the copy would be like this, here the copy would be like this. You mirror on this edge, so copy would be like this, copy would be like this, so either in mirror, make periodic, filled with zeros. But you have to take a decision of have this outside. Okay, yeah, all these details of sizes and so on. Okay. Yeah, here are some examples of image rotation and the thing that play with the relation. So let's say that you have this image. You want to rotate. So this one, it is the same one, but simply it has been rotated. And now you compare, the cubic is the most accurate interpolation. So you compare what is the difference between B cubic and nearest neighbor. This is the difference. You see that the differences are mostly where H is at, and that makes sense. So if, let's say that you have a very flat region, the pixels in some particular number, like this one, they are all take almost the same value. In the limit, they take exactly the same value. So exactly the same value, the cubic minus nearest neighbor is 0. So that is why you have the main differences where regions are not flat. The same nearest neighbor minus linear. You can have kind of comparison. The cubic is the most accurate, the linear, and then the nearest neighbor. We have other comparisons here. And also these geometrical transformations, they can use them to make very fancy transformation. And this is one of them. So let's say this goes to some cameras. Some cameras. For instance, this camera, the setup, but let's say that you want to have a panoramic view of sample. So what you can do is the following. So you can push back the camera. So let's say that this is our camera. Here, there is a spherical mirror. So what you record is the image in the spherical mirror. But then what you have is 360 degrees view of the sea. It's because everything is projected here. Everything is projected here. And then you are recording the mirror. So this is a mirror. The camera that is just the camera, but it is looking at the mirror, at the spherical mirror. How can we simulate that? Simulate that this way. So let's say that we have a square image, standard image, okay, and we want to simulate how this would be seen in this mirror. So you can define this transformation. Okay, so you have for every point you need to know where for every point in the output you need to know where it is coming from in the input. So we will do the following calculations. You take the coordinates of the output point and you compute rho. You see, this is just a polar transform. This rho and theta, they are just a polar transform of R out, C out. So this is the length and this is the angle. Now, we will compute another angle that is rho divided by rho naught. So what is rho naught? Rho naught is the input image has some size, the output image has some size, this one. Then we compute the minimum of the number of rows, number of columns, and divide by 2. And we take this length divide. So this is the kind of normalization. Then we compute the other sign. This is okay, so we have the polar coordinates and the next term. Okay, so now we come to here. Now you compute these again, it's kind of similar normalization factor, but now for the input. And now you compute D, and D is this normalization factor times this angle times 2 divided by pi. Okay. And now you have theta, and D are the new polar coordinates in the input image. So now you simply undo the polar transform. Now you have the coordinate in the input, and now you interpolate there. Okay, so you can see that you are not restricted to just very simple transformations like the multiplying by a matrix, or rotation is also multiplied by a matrix. So you're not restricted to that. You can define a very convoluted way, go from the output to the input coordinates. And you can simulate this kind of stuff, or you can do whatever with your images. So in general, it is geometric transformations. This is the main idea here. So how to go from coordinates in one image, coordinates in the other one, and then this is just changing the geometry of the space. Any question? No question? Okay, so then let's start with the next lecture, that is uncorrelated noise. So uncorrelated noise is when you have a perturbation in your ideal image. So typically, we will assume that the noise is additive. It doesn't need to be additive, but most of the time, or in many physical systems, it is. So you have an input image, then have some noise, then that's what you observe. It's the ideal one, plus noise. And this is valid for metrology. So I have not written the arguments. This one is valid. This noise, it changes from point to point. And this noise can be correlated or uncorrelated. Now, what is the correlation? Correlation of the noise and even that expected value of the noise. Noise is the mean of noise is supposed to be 0. Okay. And then we have noise. So what is the correlation? It is this expected value. For this to be true, we need this. Otherwise, you have to subtract the mean. Okay, so let's say that it is uncorrelated noise. So if it is uncorrelated noise, this is N. That is. Then you have the variance of the noise, and this is I. This is a vector. I have made it 1D because it is simpler to draw, but it is in any number of dimensions. Okay, so this is uncorrelated. Okay. What if it is correlated? It's correlated. Then the noise correlation points. Now this is organized. Then it has the values. Something like this. And it's symmetric. Let's go. This is a correlated noise. And correlated noise means given if you give me the noise value at a given point, I can tell you something. I cannot predict exactly what the noise will be, but I can tell you something about what the value will be. I can tell you more or less the region where it will be. For uncorrelated noise, I cannot. You give me the noise value at a given pixel, I don't know what will be the noise value in any other pixel. Let's see a difference. So these two images, this is uncorrelated noise. So given a point, this is noise. So given a point, I cannot tell you at all what the nearby values will be. But this one, this is also noise. These are random. But if you tell me that the noise at this point is this one, the next one will be nearby. So I don't know exactly where, but I know it will not be too far. So this is a smooth correlated noise. Okay, so which are the noise sources that we have? So, for instance, in electrical interference with a sensor or a nearby source or whatever, these half-tone distortions, when we were thinking in with these rosets, we will bring that at some point. We have some moire pattern. So, so given a noise at the point, I can tell you if I rotate 60 degrees, what the noise is. Uncorrelated noise is coming from quantum noise in the cameras, the size of the grain of the film photography. There is a silver aligned grains. There are small crystals of silver. And then the size of the crystal makes uncorrelated noise, or the neural noise in the retina, or quantization noise is so uncorrelated. So we have these two kind of sources of noise, and we will care now for the uncorrelated. Okay, so this is our image formation model. So you have an ideal image. This is the one that you would observe, and that is added to noise. And if you make the Fourier transform, you get the same Fourier transform of the noisy is the Fourier transform of the ideal plus the Fourier transform of the noise. And here is some examples of how uncorrelated noise looks like. So this Gaussian is uniform, is salt and pepper, these are distributions. So you know these things is different from correlation. So correlation is one thing. The other one is what we are seeing there is what is the distribution of the noise. So, and these are two different things. This is, if you look at a single point, how it is distributed. This is, if you look at the pair of points, how they are related. Okay. So when you say I B noise, say this, they're saying independent. The first I, and the second I is identically distributed. This is IID. Identically distributed refers to these independent variables. This is this one. So this is Gaussian, salt and pepper, uniform pepper. This is correlated, not correlated. You have seen this expression before, IID, right? So, but they refer to two different properties. The ID is how a single point is distributed. The first type is how pairs of points are related. Okay, so this is how Gaussian noise looks like. So this is the probability density function of noise. Say for if it is uniform, say it's solid and pepper. And the same for color images. So you can have noise, Gaussian noise, the three channels, red, green, and blue. They are noise, they are Gaussian noise, they have Gaussian noise. And then if red, green, and blue are Gaussian, the luminance is also Gaussian. If it is uniform in X, Y, and red, green, and blue, it is also uniform in luminance. And this is an example of noise Gaussian noise. Let's stop here. Make a break of 10 minutes. Yeah. Okay, this is just an interpretation, a reminder of the interpretation of the histogram of the normalized histogram. So if you divide the histogram by the number of pixels, it's an approximation of the probability density function. So that is, even if I take a pixel at random here, and take a random location, what is the probability that it takes a particular value? So what is the probability that it takes the value 175? So is the histogram of 175 divided by the total number of pixels of the histogram is an approximation. It's an approximation of the probability. And this is the autocorrelation. The autocorrelation here at the definition of the autocorrelation. It is the same that I have given here. There are a couple of differences that we already know. So the definition he has given is this one. Five. Five, four, five. Let's try to make the size of the notation. Okay, so let's see what are the differences. First difference is it has defined I in the as I minus B of I. This is the first thing. So the correct definition of the autocorrelation, you have to subtract the mean. That is why I was saying down here, for these to be true, we need that the mean is 0. Okay, so that is the first difference. Second difference is this side. The difference is this side. And this side, what tells you is have an image, have a notation R, have a notation R, M. Okay, so if R plus M is inside the image, that's fine. What happens if R is in the border? So if R is in the border, R plus M is outside the border, so I have to do something. So what can I do? Typically, what you do is you take these times. In fact, yeah, this is wrapping. And you know many other strategies like mirroring or whatever. The one he has chosen is wrapping. This one here with the modules is wrapping. Okay, so yeah, this is auto-population. Some examples of auto-population. So if it is independent noise, white noise, then we have this auto-population. It is not very strictly zero. See that there is a little noise here, but this is normal. So 5 is normal because of this expectation. So for this expectation means you take white noise, you repeat this white noise forever, and then you compute the average of all these realizations of noise. But we don't have infinite realizations of noise. We just have one. So with one, you can look at factor 0 here. So you get a little bit of noise. And if you take many realizations and you average all these auto-population, then this will go to 0. Okay, and this is the auto-population, the power spectrum. The power spectrum, you know, with this power spectrum, it's using all the time it's using all the time the modules, but yeah, but deterministic, so whatever. So it's using all the time the deterministic approximation. So you know the power spectrum of an image at a given frequency is the Fourier transform of the auto-population of that image. Remind always that the argument of the auto-population is lag. Okay? This is not R. Okay? It is the lag. Okay, so you take the auto-population, you do the Fourier transform. This is definition of the Fourier transform. One definition is also so by definition it is this. Now, if it is deterministic, I is deterministic. It's always the same picture. There is no noise. There is nothing random there. Then it is the Fourier transform of the image at that location. But only if it is deterministic. If the power spectrum is defined like this. So you make the Fourier transform of the auto-population, this is what you get. Almost a constant. Now, that is why it is called white noise. Because white light is supposed to have this effect. Right? You have the same energy at all frequencies. Okay, so this is uncorrelated noise. But let's say that we have this image. This part is deterministic. We have this noise. So this we will corrupt this ideal image with this one, and then we will get our observation. And now we can look at the Fourier transform. So Fourier transform is something we need, but let's make cut in the profile so that we can see it as curves. So this is the power spectrum of the ideal image. It looks like right? It's not noisy. This is what we represent exactly this one. And I remind this behavior that typically they follow as 1 over frequency squared, at least frequency to some powers, 1 over frequency squared. But independent noise, it is flat. Okay, so when you add the two, so let's say that is okay, that's n, and then you subtract the image. Now you wonder, okay, what is the power spectrum J? This is the power spectrum Y. That's the power spectrum of J. And for this to be true, there is a condition. That is I and N are independent. They are independent. The two power spectra, they are. Okay, so now we have the power spectrum of the I, power spectrum of the noise, and we add the two. And this is what we are adding. So we are adding the power spectrum of the ideal, the red one, with the power spectrum of the noise, that is the blue. So you realize that there are frequencies for which you have more signal coming from the ideal than from noise. And there are some other frequencies where you have more signal coming from the noise than from the signal. So if you want to make a low pass filter, this would be a good region to put your pattern. Because from this point on, the signal to noise ratio is smaller than 1. Signal noise ratio is defined like this. Signal to noise ratio is defined as normally I don't put the arguments, but I think here it is important. Signal to noise ratio at a given frequency, it is the power spectrum of I that frequency divided by the power spectrum of the noise at the same frequency. So from this point, the signal to noise ratio is smaller than 1. If you want to make a low pass filter, this would be a good kind of. Okay. Yeah, so we have said the Fourier transform is the 2D. This is the 2D Fourier transform of the ideal. This is the 2D Fourier transform of the noise. Then these representations here, they're just one line. We take one of the lines, and we plot. And this is the denoising one. So you see that at high frequency, all this information is buried in noise. So I cannot see that information anymore. I can see these lines anymore. They are below the level of noise. And at low frequency, I can see the information level again. And then we can mark which are the coefficients that have more noise than signal. These are these blue coefficients. And we can do the opposite. More signal than noise is this coefficient. We know for this particular image because we have simulated the noise. In real life, we don't know. But the same concept applies. So we have an ideal image, we have noise that we don't know which one it is. But then what you know is there will be some coefficients where you have more power coming from the signal, and there will be some others, but there is more power coming from the noise. Okay, so this is another example. Same idea for the thing. Okay, so we want to highlight the signal. So this is the distribution. The red points are the distribution of the regions where we have more power coming from signal. So you want to make a low pass. You have to choose simple, because that is a low pass filter. You have to choose a simple. And the radius of the signal has to be such that most of the content is coming from the signal. Still, you are having regions, you have more noise than signal. All these coefficients have more noise than signal. So choosing the right, so if I make it smaller, say that I take this radius and make it smaller. If it is smaller, then I'm leaving out a lot of signal components. But it isn't always a trade-off. How much noise you let it pass. Okay, so this is here. Now you apply a Gaussian filter, for instance. This is what you get. So now you have less noise, but also less signal. So that is why it is black. Okay. This one, let's say that you are a magician, and then you know exactly where you have more signal than noise. And this is the shape of your filter. So for this image, I will multiply by this filter. It is a low pass because most of the frequencies are coming from low pass, from low frequency. But it is much more than that. It is not this compromise. Here, I'm not a magician. I play with the different radii, and then I see where it looks better, where I start to get a lot of noise. But here you're a magician. You know exactly where you have more signal than noise. And now you apply that filter. This is what filter, and this is what you do. That it is much sharper than the original low pass filter. So the low pass filter look like this. New one has sharper edges. But here you need to know exactly which coefficient Fourier space has more signal than noise, which is not easy. Okay, so yeah, this is the comparison. And still, we are losing signal information here because it goes below the level of noise. Okay, so let's try to design a filter that is a better approximation to this one than to this one. Okay, so here you need it exactly which coefficient has more signal than noise. Okay, so let's try to approximate that. And on the way, we will also complicate a little bit more the image information mode. So now we will have a point estimate expansion. So the system will go, system will do like this. Our previous system, this one was I goes okay, goes directly. In the new one, you have J, 6, 5, all dates from last notes. So we will have I goes my filter, then that notes. So now there is a filter in between. So now the question is, if you give me J, can I pick override or an approximation to I? This is what we have done with the low pass filter before. So it gave me the noisy filter, and I have tried to recover the original. So let's try to do it. This is our image formation. Point spread, you know, where it's coming from of it. So depending on how your optical system looks like, you have a bigger or smaller point spread function, different point spread function. So We have seen this before. So the point spread function of an optical device will blur the picture. So all this you have seen before. Okay, so this is our image formation. The graphical representation of image. I decompose something. Here in the example, it is a Gaussian, but it doesn't seem to be. And then you have convolution, and then you have noise, and then you have a noisy and convoluted. Now, let's do Fourier transform. So let's do the Fourier transform of this equation. Transform. This would be Fourier transform of K. The Fourier transform by the convolution becomes a multiplication. Noise. Okay, so we do Fourier transform. This is what we get. Good. And now the same system, but in Fourier space, looks like this. We have the Fourier transform of the eye. This is a Fourier transform of H. We multiply point by point. We have the Fourier transform of noise, and then you add point by point. Okay, so let's try to recover it. For recovering, what we will do is we will follow this path. So let's say that we call this index K. So this one here, this one here, we call it K. And then if we call it K, the new system is K plus 9. This is the same as this one. Let's try recover K. Okay, so now we have K, J, that is the observation, is K plus noise. So now we will apply the filter W to J. Okay. And then once we have K, so if I try to recover, I will apply the filter W to J, try to recover K. Once I have recovered K, I have simply to divide by H, and that will be so you take J, you try to estimate K. Once you have K, you simply divide by H. Now what you want is that your estimate of I is as similar as possible to the estimate of the 2I. So let's do this. So let's move. So I for the natural and multiplied by H. Okay. Okay, so the first step will be by running out of symbols. Okay, so let's say this is tilde. Tilde is our estimate. Okay. Normally our estimates are angles, but angles are Fourier transform. So tilde is our estimate. This will be a filter that we have to figure out which one it is times K. Once I have K, I can give one more step back. Then I can estimate by K, an estimate of K divided by H. So we will do it in 2 steps. And I want and this may be similar by similar. And I have to quantify that. So what is similar? Similar is and complete the difference. So, and this is in the Fourier space. But if this is in Fourier space, I can Fourier plan and have an image. Different. That is good. You estimated, you started with an idea. Have tried to estimate. Okay. There is a difference between the two. Okay. Okay. There is a difference between idea and your estimate. Now, when would you say I have made a perfect recovery? When this is zero everywhere. This is zero everywhere, then I have made a perfect recovery. This will not be zero everywhere for sure. But then what I can try to do is the power of this. Power of this is the sum or all of the exponential. Do you agree with that? That's by power of the value. This by Parseval is the integral over all frequencies of remember that. Okay, so this is simply saying the energy in real space is equal to the energy in Fourier space. This is a value of frequencies of two image and minus the six actual molecule. And we want to minimize this. This I want to be minimal. I have to find, and this depends on what, which is the only parameter that I have in my system. So this is a parameter. H is not a parameter, but H is a given. So these minimizations performed with respect to W. So that's why this so that we highlight the dependence on W. It's not under that or right? 9 minus 1. Okay. So this was W. And by that's okay. I mean, this is the reality. By so J is given, H is given, I don't know. And all I can change here is this W. Now we wonder, how can I minimize something if I don't know this thing? This I don't know. I don't know. All the others are now. All these are now. I've seen this image and I know what how the point spread function looks like. But I don't know how the original image looks like. It looks like. Okay, so it is a kind of mathematical figure. Okay, so let's go. So this is the result. Okay, so we don't. Let's pretend that we know it. So if we pretend that we know it, then everything is now 9 can solve for that. So I can derivative sigma squared but of this with respect to W. This is a little bit complicated because we have complex numbers and there are differentiation rules to complex numbers. So can be done. We will not do it, but this is the logic. You start with this. Start with this. Then what is the filter? Filter is this one. So let's write. So this is pretending that I know. Pretending that I know. Sure. Yeah. So you notice that your camera has done this. So your camera had an ideality, applied a pointer square function, added noise, and then this is what you observe. Okay, this I know because I have seen it. This I don't. And this I don't. And this I know I have to characterize my camera. And then what I will try is to design a filter such that from J I can approximate I. Okay, so we were saying the solution. The solution of this is this one. So we can be proved, right? Actually, it's not too difficult to do it, but we will do it. The solution is for every frequency. It's A star at that frequency times module I at that frequency. Right? I divide by A. That the frequency squared I at the frequency squared as so this is the solution. Pretending that we know what the equilibrium is, but we don't know. But now we divide on both sides by I squared. I don't write the argument anymore, but it is here. Now we have realize. So this term here, this is one over signal illustration. So now we can write image as So now we are in a little bit better position. So let's look back. So we wanted to minimize something without knowing the input image. This was difficult. I cannot do that because I don't know what the input image is. But now, what you're asking is not this is the derivation. We will skip the derivation. But now, I'm not asking for what is I. I'm asking for what is the signal to noise ratio. And this is a little bit better. So you don't have to tell me exactly. You don't have to tell me exactly what I and N is for every point. But you have to only tell me the ratio of these two versions. So you tell me the ratio, I'm asking for a little bit less relation. So you have to characterize somehow this this ratio. What is the signal to noise ratio over all frequencies? But this is something that you can do. So you don't need I, but you need this signal to noise ratio at each point. It's a minor condition. And now you can fit that. Once you have it, now you have W. So all you have to do is multiply W by J, that is your, and divide by 8 squared by 8. Then you have estimated one. Now you follow this recipe. Once you know W, once you know W, you come to here and you follow your recipe. So W times J and then divide by 8. That is your estimate. Okay, so let's see how to do this in practice. Okay, so let's say that this is our image, this is our noise perturbation, this is the noisy observation, all the spectra, so the original spectra, the noisy spectra, and you estimate the signal to noise ratio at every point, and this is the mean amplitude. So this is how W looks like. See that you try to recover this line. So in this line, you think that you have larger signal to noise ratio, and you don't try to recover this route. So you think you have a very low signal to noise ratio, and at low frequencies you have high signal to noise ratio, and then you try to keep it and so on. And then you multiply the noisy times with the W. This is what you get. And you see this project is similar to the original. So now if we look at it in real space, it's how they look. It is not perfect, there is noise, but it is much better than anything else that we have done so far. And this is with just a Gaussian. Oh, yeah, this is what happens if you have a filter in between these eight. Okay, so now we have this filter, and this is the this is original, this is version. Now your filter looks like this. Why? Because your original signal, this one, for the one that was black, it had very little signal to noise ratio. Let's look at these things. Let's look at K. So K So H was multiplied by Gaussian. So at very high frequencies, we have killed information. So at very, so now this one doesn't have, this one doesn't have high frequencies, while the noise has. So we want, in this signal to noise ratio, we need it here. Signal to noise ratio would be very low because if you have multiplied by something that is killing the information. So this age is killing the information. So somehow this part takes into account for this information kill. Now this is how the benefits spaces. So the very high frequencies that have killed all the information there, but you cannot over it. This was the original, this is the after peanut filtering, this is the original. So the high frequencies we cannot recover. They were killed by the low pass filter. And then this is the peanut filtering. This was the noisy. This was the you can't compare everybody. You have lost all the edges. It is normal. Any question? By the way, this technique is also called least mean squares. Least mean squares. Okay, so let's say that we have this picture and we want to apply the Wiener filter to it. So we have to estimate the signal to noise ratio. How do we do it? You go to a region that is pretty flat. And there, what you should have is depth noise. So you take that region and you subtract. Okay, so the original, it may have a gradient. It may have a gradient of light or a gradient of painting or whatever. So this part might be brighter than this. So we want to get rid of that. And we know we are having all the time this effect. Now we are in the world, okay? We are in the world, and we have this effect. Okay? So now this is the wall, this is noise. But the wall is very low, it's very, very smooth. So that means that it's really, really just low pass filter signal. So what we do is a high pass. So this is a high pass. You take the original, do a blurring, and then you compute the difference of this high pass. So now you're keeping just the constant part of the power spectrum, and you can estimate what is the noise, the different channels. This is the noise in the different channels. Okay, so now we know what the power of the noise looks like. Now, let's take a very small point in the image from here. There is a reflection of the flat. So this should be a point, extra point. But it is not a point, it's a spread. So the point of spread function. Now you estimate the point of spread function of that very black point. Okay, so now we have the PSF. Now you construct the filter. So noise is flat. The point of spread function looks like this. An approximation to the signal to noise ratio, the power of the image. This would be the power of A. You approximate the power of I by the power of A. Then you can construct the filter like this. This was this is filter. And not this is original, this is filter, it's less noise, and this is the same filter with manual. But these things you can estimate. You can characterize your system, what is the DSL system, what is the noise of your system. Then you can estimate what's the signal condition.